Hello everyone and welcome. In this lesson, we're going to be discussing the end behavior of rational functions. First, what's a rational function? Well, it's really any function that's created by the division of two polynomials. Now note, the bottom one can never be equal to 0 because then we'd be dividing by 0, which in math is undefined. Some examples of rational functions include this, and this. But we might get something that doesn't seem rational at first, but if we rewrite it or use some of the rules we've seen in the past, we reveal that it does in fact meet the criteria we're looking for. Some non-examples include this. Although similar to our first real example, this is actually not an example because it could be rewritten as a linear function if we divide each term by 2. And radical functions, which we'll be seeing later, aren't in fact rational, so they serve as an example of something that isn't what we're going to be working on now. End behavior. Now, rational functions are created by dividing two polynomials. And the graph of a rational function can sort of be thought of as a result of the battle between the two functions. So they're fighting it out, the numerator and the denominator. The function with the larger degree is going to be stronger than the other function and will have a greater influence on the overall shape and behavior of the graph, especially for very large and very small input values. So essentially, as we're going out towards negative infinity or out towards positive infinity on our graph, the polynomial with the larger degree is going to have more of an influence and sort of dictate how the graph behaves. It's going to win the battle. Here is our sort of rules to follow when we're deciding what the end behavior is. If the degree of the numerator is greater than the degree of the denominator, that's going to tell us that the end behavior will be similar to that of the simplified fraction that results, and we'll see some examples of that. If the degrees are equal, the end behavior will approach a horizontal asymptote. We'll see another example later. And if the degree of the numerator is less than the degree of the denominator, well, then we're going to be dealing with another horizontal asymptote, specifically at y equals 0. That is always going to be the case. And let's look at some examples now to see these in action. So here we have a polynomial, and the degree of the numerator is greater than the degree of the denominator. So the end behavior is going to follow the simplified function of the leading terms. So we're going to take the leading terms and simplify, and we get a linear function. Now this is a positive linear function, which means as we go towards negative infinity, it's going to decrease, and as we go towards positive, it's going to increase. Therefore, our rational function is going to follow that same behavior, decreasing as we go towards negative infinity and increasing as we go towards positive infinity. If we look at a graph, we do see that that is in fact the case. In this example, the degrees of the numerator and denominator are equal. So we're going to approach a horizontal asymptote as determined by the ratio of the leading terms. So if I take the leading terms and I simplify them, I'm going to get 2, which tells me that as we go all the way to negative infinity or positive infinity, the function is going to get closer and closer to 2. And here we have a stretched out visual of the graph, and we see that all the way on the left and all the way on the right, it is in fact starting to level off at y equals 2, approaching it and getting closer and closer. Last but not least, example 3. Here we have an example where the denominator degree is greater than the numerator's degree, so we're going to be approaching a horizontal asymptote at y equals 0. It sometimes helps to simplify the leading terms, but when you do, you're going to see the same thing again and again and again. Nothing on the top, nothing in the numerator, and a value of x, some term with a variable in it on the denominator. And when we run into that, it's always the same case. The end behaviors are always going to be 0. And if we look at the graph, that is in fact the behavior that we see. Thanks. I hope this video was helpful and that you visit us again. Thank you, everybody.